In this presentation we are going to have a look at the basics of aspects of virtual geometry, what is used, what do you mean by virtual geometry, and where we can use virtual geometry in Gambit. So let's start. So as till now we have, I guess, seen something to do with the real geometries. So there are three type of entities possible or available in Gambit. One is real entity, other is called as virtual entity, and third is called as faceted entity. The real entities are nothing but, most of the time, whatever the entities that you create using Gambit operations, those will be real entities, or whatever the entities, some entities that while doing import operation, some entities will also have a real representation. So the basic definition of real entity is the entity which possess their own geometrical description. It means they have their own mathematical description of a geometry. So all the real entities which are available in Gambit, all those real entities will have their mathematical definition present. But if you talk about virtual entity does not have any mathematical description, but what they do is they rely on the faces, or so they rely on real geometries for their representation. For example, again, if you talk about the table, like if you see, imagine that there are two tables and there is a gap between the table. The table is nothing but real entity. It means it has its own mathematical representation, it has its own form, shape, and everything. Now if you put a tablecloth on the tablecloth as such doesn't have its own geometrical representation. What it does is, for its shape, it relies on the tables which are underneath. So we call tablecloth as a virtual entity which relies on the real entities for its definition. The third type of entity available in Gambit is nothing but faceted entity. The faceted entity is nothing but which always relies on the underlying mesh which is there. It means whenever you import a mesh and if you want to extract a geometrical information out of it, then the geometrical information will be in terms of in the form of faceted entities. So the third type of entity is nothing but faceted entity. So this is the main difference between real and virtual entities. Virtual entities, as I said, they don't have their own representation. Real entities, they do have their own mathematical representation. So the difference between the operations for real and virtual entity is nothing but, if you want to create one more real entity, then it has to have it means if I merge two real entities, it will create one more real entity, and all these operations which are there, which are applicable on real entity, they will create or modify the topology of the entity. We'll talk about the topology later. Virtual geometry operations can employ any combination of real and virtual entities. It means if you want to create one virtual entity, you can use combination of real or virtual entities. Down the line this point will be more clear. These are the basic tasks that you can do on real geometries. Like you can create real geometries. For example, you can create real vertex which has its xyz coordinate. You can create a real line, straight line, which has its own mathematical representation. You can create a real volume, or you can create a real face, or you can modify also all these geometries. It means you can split one edge into two edges, you can split one face into two, you can do a boolean operation on real entities, and you can do a blending operations on the real entities like fillets and all. If you talk about the virtual entities, on virtual entities, creation of virtual entity involves virtual vertices, or maybe it involves virtual entities, formation of virtual edge, face, and volumes, the shape of which are defined by the existing entities, existing real entities. And this is like modification you can do. You can do a repositioning of virtual entities, you can do a splitting operations, you can do a merging operations, or you can do a collapsing operations. If we see, boolean operations are null, like boolean operations like unite, subtract, and intersect, they are not available on virtual entities. So that is one more limitation of virtual entity. So if you want to do a boolean operation, you have to have real entities, and because virtual entities, they are not possible. So the idea behind virtual entities, or using virtual entities, you finalize your geometry, you do all the major changes that you want while working on real geometry. Once the geometry is finalized and now you just want to close some gaps, or now you just want to decompose the geometry for meshing, then you use virtual operations. So that is the basic concept behind virtual entities. Basically there are two you can say representations of every geometry that you create in Gambit. One is called as foreground of the model, other is called as the background of the model. Foreground of the model consists of topological entities that are observable upon direct examination of the model. It means if I create some geometry in Gambit, for example if I am creating, let's say, a cube in Gambit, this is nothing but the foreground of the model. So whatever you see in the graphics window, whatever the thing which is displayed in the graphics window, that is nothing but the foreground of the model. So that is the foreground of the model. There might be a background of this. We will see what is the background. It reflects the outward appearance of the model both in shape and structure. Whatever we have seen, a cube, so foreground of the model, it reflects the outward appearance of the model in both shape and structure as well. The background of the model is nothing but the topological entities that are not directly observable. It means if I have a look at this model right now, there might be a background. In this case there is no background, but in virtual case there will be a background. So background of the model is nothing but that is not observable here, but that is present in the background. So that is nothing but the background of the model. We'll have a look at what is foreground and what is the background. The background is nothing but, you can say, a core structure, core frame. So that is nothing but mathematical definition of which defines the overall shape and the structure. It means, again, if you talk about the tables and tablecloth, if you see, the background of the model is nothing but tables, two tables, which actually defines what should be the shape. Now the foreground of the model will be nothing but the tablecloth on it. So if you observe, what you see is nothing but the tablecloth. That is the foreground of the model. What you don't see and which defines the structure, overall structure of your geometry and all, that is nothing but two tables which presents in the background. So background is the most important to define this geometrical shape. Now imagine that you have this kind of a case. Let's say this is a age loop, continuous age loop of 6 edges: age 1, age 2, age 3, age 4, age 5 and age 6, and there is a common vertex between all these two edges. So it means all these edges are connected to each other and they form the closed loop. So vertex 1 is common between age 1 and age 6, vertex 2 is common and between age 2 and age 1, and similarly for all other edges. So if you see what is the foreground of the model, if you see right now, what we see is nothing but 6 real edges connected to each other, forms irregular planar hexahedron. Yes, each edge and the vertex possesses its own geometrical description. It means if I go and ask to this edge, who are you, it will definitely have its mathematical representation. Or if I go and ask this vertex, who are you, it will say that I am a real vertex, I am a vertex and I have these xyz coordinates. That is what it is going to answer. So each edge and vertex possesses its own geometrical description. Each entity has their mathematical representation. Everything is there, all the mathematical representation, geometrical representation, everything is there for this. Now let's say I am going to do one operation which is nothing but virtual merge operation. So I am going to do virtual merge operation. We'll see what is virtual merge operation. In that case, imagine that I am just going to merge the two edges. For example, I am going to merge age 1 and age 2. So if I do this operation, what happens? Whatever I see, and imagine that is a virtual merge, whatever I see in the foreground is nothing but v underscore age dot 7, v underscore because it's a virtual entity, then vertex 3, vertex 4, vertex 5, vertex 6 and vertex 1, and similarly the remaining edges. That is what we see in the foreground of the model. That is what we see in the foreground of the model. But now if you see, this is a virtual, it's like a tablecloth. Now if I go and ask this tablecloth, or if I go and ask this age, who are you, it says that, boss, I don't have my own definition, I don't have my mathematical formula with me, but what I do have is, I do have two edges behind me which are supporting me. I do have two edges which are actually determining what is my shape. So that is what the background of the model is. So v underscore age dot 7 does not possess its own geometrical description. Its shape is defined only by referencing to the geometrical description of age 1 and age 2. It means that is nothing but the frame. So that is the background. So v underscore age dot 7 is overlay entity that represents the specific set of edges to which it refers. Which entities will be there in the foreground and the background, or which entities have a real representation and which has the overlay representation. Now if I have a look at the foreground and the background of this is actually before there is a foreground. Before doing a merge operation, this is the foreground. It means in the foreground I have real vertices, I have real edges, they do have their own representation, mathematical representation. So they are not, I need not to store anything in the background because they define their structure, they have their own definition. Now after doing a virtual merge operation, what has happened? One vertex has gone in the background. If you see, that vertex is a common vertex. If you see this vertex 2, that vertex has gone in the background. That is the first thing happened. And now what else has gone in background? Again age 3, age 4, age 5, age 6 is there in the foreground, and v underscore age dot 7 which is created after merging, that is in the foreground, and this is in the background, age 1 and age 2. This is like a table frame and this is like a tablecloth. So that is what is there in the foreground and that is what is there in the background. So basically this v underscore age dot 7, it doesn't have its definition. It is relying on this age dot 1 and age dot 2. This is actually the background, or these two edges has its own definition. This doesn't have its own definition. It relies on these two edges. Now if you see, these two edges are not present in the foreground. We don't see these two edges. If you see here, we don't see this age dot 1 and age dot 2. What we see is v underscore age dot 7. So that is nothing but the foreground of the model. So this is the concept behind foreground and the background of the model. Now this is the most important point as far as the capability of virtual geometry is concerned. What Gambit does is, Gambit display and meshing operations involves only those topological components that exist in the foreground of the model. It means whatever the criteria, let's say meshing criteria are going to be evaluated, or whatever the validity criteria, like our geometry should be watertight geometry. This is one constraint from meshing side. So whatever these constraints, all these constraints are going to be evaluated what presence in the foreground of the model. Gambit will not go to the background to evaluate this constraint. It means it might happen that, for example, in this case, it might happen that in the real case, let's say there is a gap between these two edges. Now what I can do, I can actually merge these two edges, or I can connect these two edges virtually. It means I am not going to create one more geometrical entity here. What I am going to do is I am just going to connect these two virtually. It means I am going to put the tablecloth on it. It means although there is a gap between two tables, if I put a tablecloth on both the tables, what I see is there is no gap between the tables, and whatever the Gambit is going to evaluate is nothing but the tablecloth for meshing constraint. It means for Gambit, this geometry is a watertight geometry, although it's not really, but by putting a tablecloth we can make it as a watertight geometry. So this is the most important concept as far as the strength of the virtual operations are concerned. So all Gambit display and meshing operations involves only those topological entities that connects in that is present in the foreground of the model. For example, in this case, imagine that in the first case, imagine that this is the foreground of the model, in which there are real edges, edge 1, 2, 3, 4, 5 and 6, and there are real vertices. Now if I am going to do a meshing on this, what happens is Gambit always puts nodes on the boundaries, and the vertex is nothing but the boundary of the edge. So what it will have a constraint that it has to put node here. There is no other option. But if I merge these two edges into one virtual edge, if you see, again geometrically they are same, but topologically they are not. There is only one edge, here there are two edges, there is only one edge. So what Gambit does is, I am going to select this edge. Gambit may or may not put the node at this point, because there is no point, vertex present in the foreground of the model. For example, let's create this geometry. What I will use is, I will use the graph paper so that I can create this geometry fast. Again, I want it in XY plane, update the list, Y, update the list, and I will say apply. So what I got is I got the graph paper. Now I can use control click for creating vertices. I can always do that. I can use control click for creating vertices. So again I said control, for example click. Here there is one vertex, one more vertex, one third vertex, fourth vertex, fifth vertex, and sixth vertex. Let's say we are done with the vertex creation. So I will make this graph paper off, apply, and now I can go and create the edges. So go to geometry, edges, straight edge between the vertices, select this vertex, this vertex, this vertex, this vertex, this vertex, and this vertex, apply, and this vertex, apply. If you see, now what I have is I have this geometry. Now this is a real geometry. It means it has its own representation and everything. Now if I am going to do a meshing, if you see, what I have is this edge. I will say okay, I want to have, let's say 10 points, apply, and this edge I want to have again 10 points, and apply. Now if you see, what it has done is, right now it is not visible, but we can have a look at it. Let me try. Like I will say all vertices should be off, apply, and now I can go to edge summary. I will say this edge, nodes, and node labels, pick, I will say all. If you see here, there is one node, the number of that node is 2. So there is one node created at this point because there was a vertex, and that vertex was, in fact, there was a vertex. So let me activate the vertices now. There was a vertex here, and that vertex is actually a boundary of this edge. So definitely Gambit will put a node there. So that is the constraint. Now if I am going to merge it, so I will just do undo for meshing. Now I am going to do a merge operation, and now I am going to do a virtual merge operation. So I will go to geometry, edge, and this is the merge. So I will say merge, and now I want to merge it virtually. So I will say this edge and this edge, and apply. If you see what has happened, geometrically if I have a look at it, the geometry is now made up of this single edge, edge 2, edge 3, edge 4, edge 5. Now these yellow edges are, they have their own representation. It's a real edges. But if you see this edge which I have created, this edge is a virtual edge. It means it doesn't have its own mathematical representation. What it is doing is it is relying on the two edges which we have used for merging operation for its definition. Now if I go and do a meshing, and let's say now collectively I am going to give 20 elements on this, because initially there were 10. So I will say 20 element, apply, and now if you see here, it has not kept any node here because we have removed that constraint from Gambit because of merging operation. So we have removed this constraint. So this is the concept of you can say virtual merge. There are a lot of other uses also of virtual merge operation. So this is what I was talking about, how virtual geometry is useful. So we'll have a look at in which cases we can use virtual geometry. We had a look at the basic definition of virtual geometry and all. Let's have a look at what is the use of virtual geometry. So before that, let's see why Gambit is there and what is the basic purpose of Gambit. Because down the line, what we are looking at is we are looking at analysis, and Gambit is, or the modeling on meshing is some intermediate step for the final simulation. So what is the fundamental purpose of Gambit is nothing but mesh, to create a mesh, and that too a good quality mesh in given physical domain. In the sense, the domain might be flow through a pipe fluid domain, or it might be a solid domain or something for heat transfer analysis. Or if I put it in other way, the basic purpose of Gambit is to create an array of mesh nodes, the location of which is represented by a specific point in the physical model. In the sense, I have to have different points which are called as nodes, their XYZ coordinates, and definitely I need to have a connectivity information so that I can form a cell in my solver. So does it really matter that how we have created a good distribution? In fact, I mean, if I talk about a solver like Fluent doesn't need any geometrical information. What it needs is, it needs the discrete points or a good quality mesh, and then it will start a solution. So it doesn't matter that how we have created a good quality mesh in a given domain. So modeling process, in fact geometrical modeling process, is just an intermediate step in creating a usable mesh or good quality mesh. So it doesn't matter whether I have created that mesh using virtual geometry or I have created that mesh using a real geometry. It doesn't matter at all. And one more thing is, like, we'll combine these two. One is to have a good quality mesh for a solver, and what Gambit does is, Gambit does not look at the background of the model, it always looks at the foreground of the model. It means if somehow we could able to create a good model in a foreground, and by using that good model, if somehow we could able to create a good mesh, then our purpose in Gambit is done. It means that will give a very good solution. It means Fluent will not look for a geometry. So what we can do is, we can use all these virtual operations to just create a good quality mesh, just to make sure that our geometry is watertight, just to make sure that we are decomposing the geometry in a proper way, so that the good mesh distribution will be created. So virtual geometry operation provides a very convenient and a powerful means of controlling the shape of the geometry, or you can say the topology of the geometry, and it also helps to mesh or to control the density of the mesh, in the sense where the mesh will be clustered, where the mesh will be coarse and all. How? Let's have a look at it. So before that, again we'll have a look at the categories of the virtual geometry based on, this is not very important, but we have to also understand what type of entities will be created in virtual operations. So based on relations, there are two categories. One is called as host and other is called as guest. Host is nothing but real or virtual entity that are in some way referenced by one or more virtual entities. Most of the cases they exist in the background of the model. For example, if I have a look at this, in which I have done a merging operation. Now if you see at the back end of this particular model, there are two edges. Here there is one edge and here there is one edge. So those two real edges, they act as a host for this one single virtual edge, which is called as a guest. So that is nothing but a host. Host is nothing but, most of the cases, like real or virtual entities that are in some way referenced by one or more virtual entity. It means those two real edges are referenced by the single virtual edge that we have created after merging, and that is why those two real edges are called as virtual edges. Now the host can be real or it can be virtual. It means right now for this single virtual edge, there are two real edges which are host. Now if I again do a merging operation, again I will say merge edge, which is for example this edge and this edge. If I merge it, now if you see I have only one edge. Now if you see, the host of these single edge is one virtual edge and one real edge. So the host can be virtual as well as real. So that is the meaning of it can be virtual or real. Guest is what? Guest is nothing but somebody who is referencing to real or virtual edges for its representation. It means in this case, what happens is, this single edge is reference, or this is single edge is referencing two edges. One is virtual and other is real, or this particular edge is referencing to two real edges. So that is nothing but a guest. Guest always references host, and most of the time they exist in the foreground of the model. If the virtual entity is referenced by another virtual entity, the host entity exists in the model background. That is correct. It means if I do a virtual merge operation, two real edges moves in the background, one virtual edge pops up in the foreground, and that one virtual edge is called as guest, and two real edges which are there in the background, they are called as host. Again, based on how the virtual entities will be created, they are also categorized into 5 classes. One is called as superset, other is called as subset, third is called as interpolant, then parasite and orphan. Let's have a look at all these classes. Superset entity is nothing but a virtual entity that references two or more real entity. Example is this. It means right now if you see, I have only one virtual edge. This is a one virtual edge. If I activate label, or I'll say check, query, and if I say virtual edge, So this is one virtual edge v underscore age dot 7. If you see, this single edge is referencing two real edges, so that is nothing but a subset, superset entity, virtual entity that references two or more real entity, that is called as superset. For example, virtual edge v underscore age dot 7 created from two real edges, age dot 1 and age dot 2. So this one edge is actually referencing these two edges, so that is why it is called a superset entity. And superset entities occupies the foreground of the model, real entities occupies the background of the model. That is true, that is correct. Another is called as subset entity, references a single host entity. It means if I do, for example, if I go and split this edge, I can always split this edge. If I go and split this edge, for example, and if I split it virtually, and I will say split into two edges, and those two edges are virtual edges. If I say apply, now if you see, these are two edges, one is v underscore age dot 8 and v underscore age dot 9. Now these are two virtual edges, but if you see, both of these two edges or both of these edges are referencing to only a single real entity which is there in the background. So these two edges are actually called as subset of the real entity. So that is the meaning of subset entity. The virtual edges constitute subset entities because they are each part of the set entities that reference by a single real entity. It means these two edges, if you see v underscore age dot 3 and v underscore age dot 2, they are both are referring to this age 1 which is in the background. So these two edges are called as subset entities. This is the most important entity, which is called as interpolant entity. Whenever you do a connect operation, it creates the interpolant entity. For example, let me create some geometry first for connect operation. So what I'll do is I'll create a square or maybe a rectangle of size 10, and now I'll copy this with some gap in between. So I'll say copy 1, translate it with, because the size is 10, so I'll say translate it with 11, so that we'll have a gap of 1 in between. So if you see, now these are two faces. You imagine that these two faces are nothing but the top view of two table. Now if you see here, we can see the gap, there is a gap in between. Now if I want to mesh it, like let's say there is a flow coming in from this side and it is going out from this side, we have to have this watertight. It means we have to connect these two. Now I cannot connect this really because the gap which I see here is large, so Gambit cannot extrapolate this face, and Gambit also cannot do this much kind of extrapolation. It cannot do. It can do it if the edges are in the proximity of 10 raised to minus 6. So I don't have any other option than creating virtual or using virtual operations. So what I'll do, I'll say connect. So these two faces, they should have a common edge in between. So I'll say connect, edge connect. I'll say connect, and now I'll select these two edges. This is single edge, first edge and second edge, and now I'll say virtual, apply. Now if you see, they are connected. They are connected in the sense now there is a common edge between. If the flow is coming in, it will go out through this. There is no gap as such. So it is like a tablecloth that you have put on the table. So now if you see the original location of this edge, if you see here, if you just observe, this is the original location of this edge, this is the original location of the another edge, and now I'll do a connect operation. So this is these two edges and connect it. If you see, it will exactly create the new edge somewhere here. So if you see, exactly it has created a new edge somewhere here. So what it does, originally there were two edges, it will do an interpolation between these two as special, or maybe interpolation for its location as well as its shape, and it will create one entity which is called as interpolant entity. So that is nothing but interpolant entity. And now if I do this operation, connect operation, virtual connect operation, if you see, there is one edge common in between, so there is no gap as such, and these things are connected to each other. Now this is only virtually done. It means there is no geometry in between the gap which was present. So if I shade it, you can see that there is a gap, still there is a gap, but only thing is, for meshing evaluation, this looks like they are connected to each other. But if I am going to mesh it, definitely Gambit will not put any mesh in this gap and in this gap, because there is no geometry available, because for putting a node we have to have a geometry. You imagine that putting a node is like putting a weight on the tablecloth, or putting a weight on table. Now imagine that originally there are two tables and there is a gap, and you are putting a tablecloth on it. Now wherever there is a table underneath, definitely you can put a weight, right, because it will be supported by table. But if you try to put a weight in the gap, what will happen? The weight will not be supported, because there is no geometry underneath it. So putting a node is equivalent to putting a weight. So we have to have the geometrical information, then and then only we can put a grid node. So whenever I am going to create a grid, it will definitely not create a grid in this particular space. For example, if I am going to mesh this, let me do a fine meshing. Let me see, the mesh interval size should be let's say 0.2, because the gap is 1, and in fact 0.5. If you see here the fine mesh is created up to this location, because there is a table underneath it, there is a geometry underneath it, but in this gap there is no node at all. In this gap also there is no node at all. So there is kind of a discontinuity in the mesh. But still we look for, still we use this, because most of the time what happens is, all these gaps which are created, it is because of the import issues. It means the tolerance value in, let's say, SolidWorks is something like 10 raised to minus 3, but if you take it to Gambit, it is 10 raised to minus 6. So things which are connected there will get disconnected here, which is something like this. Now generally typical gap that is created because of all these disconnect operations, the value of the gap, or the size of the gap, is much smaller than the size of the mesh that we are looking for. It means now if I create a mesh, I'll say, I will again reconnect it, I'll say redo, and now if I mesh these two with some larger size, for example let's say size is 2, and if I mesh it, if you see, is same as there is no gap in between. So there is one element here, there is one element here, we don't see this gap, and ultimately what is going to fluent is this mesh, not the geometry. So as this mesh is going to fluent will not see any discontinuity between the mesh, as well as there is no gap in between. So we can use virtual geometries if the size of the gap which we want to fill, that is less than the size of the mesh that we are looking for. But if there are some cases, if there is case that the size of this gap is much larger than the size of the mesh, then we don't have any other option than creating the geometry. It means in this case I can create the edge, I can create this edge, I can create this edge, and then I can go for face creation by using this. So I can fill that gap by using this also, and now I can put a node. Definitely I can put a node here. So I'll say this, mesh it with interval size 0.2 again, and I'll say apply. Now if you see, now you will get a mesh in this. So if you see right now I have all the mesh is very good. So if the gap funda is, if the gap is more than the mesh size, you create real geometry. If the gap is less than the mesh size, then you use a virtual geometry to just close the gap. And most of the time the cleanup operations are actually, in cleanup cases or data losses, those import in case of geometry imported which is created in other CAD software, the gap is very very small as compared to the mesh size. So we will be using virtual geometry to close the gap and create a watertight geometry. So this is one more type of entity which is called as interpolant entity. What it does, you have two edges, let's say this is one edge and this is another edge. If you are connecting these two edges, it will create the interpolant entity. The shape of that will be decided is nothing but the interpolation between these two shapes, as well as the location is nothing but the interpolation between these two. So that is interpolant entity, which is very important in Gambit. This is one more entity which is called as parasite entity. Parasite entity is nothing but the entity that references a single higher order host entity such that its geometrical definition is defined by that. It means the entity which is relying on the host entity for its shape. It means if I create some face, something like, for example, if I create this, let's say I have this face and there are two points which I have created on the face, and now if I am going to create the edge in between, and if I give this face as a host entity, what will happen? The shape of the edge will be also similar to that of a face. So this particular edge which I am going to create, that is going to rely on this particular face for its shape. So for example, this kind of edge. So whenever I am going to create this edge, the shape of this edge is same as the shape of the face. So this particular edge is called as a parasite edge because it is relying on this particular face for its definition. So that is called as parasite edge. And how to create parasite edge is, let's create a face for curved, because we want to create a curved face so that we'll be able to visualize the shape of the edge. So let's create a face. So I'll say reset. Again I'll use the famous or very strong function which is there, nothing but using a graph paper, grid, display grid, and then I will use some you can say for creating a curve like sinusoidal curve, I will create some points. I'll create some points for creating a sinusoidal curve. Then I have created points, so let's say I don't want the graph paper, go to edge, create edge. I don't want a straight edge, I want curve edge, so I will go for nerves, and then I will select this. This nerves is nothing but a single edge which will pass through these particular vertices. So I have created edge. Now let me create a face. So I want to sweep this edge into Z direction, so face creation by sweeping operation, which what you want to sweep is this edge along a vector, define vector. Positive Z is correct, but the magnitude should be changed. Let's say it is 10. Apply, and then I will say apply. If you see, what I got is I got a face. Now this is the face. Now let me create a vertex on this face. So again I will go vertex on face. I will say create it on face, and then I will select this face, and then I can do a middle click and drag. So let's say I am creating this vertex somewhere here. I have created this vertex, I guess it is created on the edge, so let's take it bit inside. I will say undo, again select this face, drag it somewhere here, apply, again create, select this face, drag it somewhere and say apply. Right. Now I got a vertices on this particular face. So again now I will go and say wireframe. Now let's say I want to create the edge, which is a virtual edge and which is a parasite edge. So I will go to edge, I will say nerves. Now okay, I will say straight edge, and now I will say virtual, using these two vertices, this vertex and this vertex, and now I am saying virtual, and the host should be a face, so that the shape of that edge will be same as the shape of the face, and I will say apply. If you see the edge which you are creating, the shape of that edge is same as the shape of the face. So this edge is actually, it don't have its own definition, it doesn't have its mathematical representation. So if I go and ask this edge, who are you, it says that I am an edge connecting these two vertices, and my shape is decided by this particular face. So how to do that? You go here, say virtual edge, say host entity should be a face. So these are called as parasite edges. So now we can use this edge for splitting this face. For example, I'll say undo, and then I have to take this, because this edge has to intersect this face completely. So I'll project this vertex. So I'll say project vertex on an edge. Which vertex you want to project? This vertex. On which edge? This edge. And apply. Again this vertex, this vertex, this edge, and apply. Delete these two vertices because we want these vertices. I deleted it. Now I can create the edge, straight edge, again virtual, between these two vertices, and the host should be this particular face. So again this vertex and apply. If you see, I got an edge. If you see, the edge, shape of that edge is same as the shape of the face. Now once this edge is created, let's say I want to decompose this complicated surface into two surfaces. So I can always use this edge for splitting purpose. So I will go to face, split face, I will say virtually connected, face virtual, split face, let's say this face, I want to split this face with using virtual edge. Which edge? Let's say this edge. I will say apply. If you see, now what you got is, you got two faces. One is this face, one is this face, and another is this face. Now These two faces might be simple for meshing, in the sense we have decomposed one face into two faces. So this is the way you can use virtual edges for splitting purpose and decomposition purpose. So that is the one use of virtual operations available in Gambit. So this is what, coming back to the point, parasite entity. So if I give these two vertices, and while creating a edge, if I give this face as a host, then the shape of that edge will be decided by the face, and this is called as a parasite edge.